So Prandtl and Glover did it for 2D. Okay? So as soon as people start applying it for wings, they got wrong answers because it was for a 2-dimensional airfoil. That means the aspect ratio is infinitely wide. So when people try to directly apply Prandtl-Glover to a finite wing, they got totally wrong answers. In Germany, there were companies like Dornier. They were building high-speed airplanes. In England, they had Spitfire and other stuff. They were doing it on the English side channel, on the other side of the channel. But neither one of them could apply the Prandtl-Glover and apply it for the finite wing theory. So around 1946, Gothard came along. He developed a 3-dimensional extension to Prandtl-Glover rule, which is what we are going to talk about. So in your quiz, number 1, you're using the Gothard's rule, not just plain Prandtl-Glover's rule. Okay? But it uses the same process, except we are dealing with linearized compressible potential flow equation in 3D. Other than that, the procedure is very, very similar. Okay? So let's start with the governing equation. Instead of just having beta squared times x derivative and y derivative, now you pick up also the z derivative. Okay? Velocity is the d phi dx, for example, is v infinity plus d phi dx. So every component of velocity has got a free stream part plus a disturbance part of it. Okay? We can take a derivative of it. Now, the wing we want to solve is this wing. So this is what you are solving in your quiz, for example. So it's enough to solve 1/2 of the wing because of the symmetry. Okay, so you already saw that in your homework number 2. So we are going to do 1/2 of the wing. We are going to do the x-coordinate system from the nose of the root of the airfoil along this. Y we are going to travel from span direction from the symmetry plane. This is y equal to y tip. And if you cut any place, you're going to get an airfoil section like this. Okay? In 3D, the wings will in general be twisted, so different sections will have a different shapes. Okay? You may even have one airfoil here, another airfoil here, another airfoil here. So wherever you slice it, you'll get a different shape. So there, z is perpendicular to the plane of the paper because this is x. This is y, x cross y, z is coming towards you. So the wing is has got a z-axis is perpendicular to x-axis, perpendicular y-axis too. Upper surface is z upper, lower surface is z lower. Okay. We are going to use the same type of boundary condition, which is a linearized boundary condition. So rather than applying it directly on the body surface, we are still going to apply at a slit, okay, just like Prandtl and Glover did. Except that that slit comes all the way from root to tip, so it's a 3-dimensional slit. It's a long, long surface. So this is the body surface. This is a combination of camber, twist, and angle of attack. So thick body will produce a big bump. Highly cambered aerofoil will produce asymmetric shape. Angle of attack will rotate the whole geometry. Okay? All of these things are built in there. So the boundary condition is still linearized. So now instead of a d phi dy, which we used to do because this was the y-axis, now we have to use d phi dz because z is perpendicular to the plane of the wing. Again, the same thing. This is the body slope. So we are going to apply this at z equal to 0 is where we are going to apply it, which is the slit condition on the slit, okay, on the xy plane. Our hope still is to get the CP distribution so that we can get CL, CM, and so forth. Even induced drag. Okay. Now it's 3D, so we want to be able to do induced drag also. So what we are going to do is, we are going to use a very simple linear transformation, just like Prandtl and Glover did. So Gothard said, I'm going to keep phi equal to capital Phi, A becomes 1. That scaling factor becomes 1. He said, I want to go from this equation to this equation, so I can keep y to be the same, y equal to eta. I can keep my z to be the same, z equal to zeta. Then I'm going to say x over beta equal to c. X over beta equal to c. Okay? So he used a linear transformation very similar to Prandtl and Glover did. And the free stream velocity was kept the same because it's not a relevant parameter. We are interested in non-dimensional quantities such as Cp. Okay. So when he did a transformation, just like we did in Prandtl-Glover, every little phi became capital big phi because of this transformation. The only thing we had to worry about was to show that beta squared times second derivative of x equal to second derivative of c. It's a very simple chain rule type of a thing like we did before. Okay. But what has happened was, as a result of it was, in the c direction, things are changing. In the spanverse direction, nothing is changing. In the z direction, nothing is changing. That means the aerofoil is not changing in the z direction. Angle of attack is not changing. Camber is not changing. So we are taking the same section of aerofoils, same span. So in your quiz number 1, we'll have the same span as your homework number 2. But in the chord direction, everything will get stretched. Okay? So in this direction, if this was a 0.2 times b, do you remember? That was a chord. Now it will be 0.2 times b divided by beta. So it's going to be a longer chord. Same way, it will no longer be 45 degrees because this point moves back by 1 over beta. This point moves back by 1 over beta. So for the shape is going to change. You're going to have a different swept wing, different geometry. So what you should do is construct the incompressible wing, which you have done in your quiz. So every corner point in the x direction divided by 1 over beta to come up with a new wing shape. That means if you have a vortex panels for the first part of quiz, you keep the same y and z for all the corner points, 1 and 2 points. The x point will be divided by beta. So that's what would happen. Okay. Very simple change. Okay. All right.
So, sorry, excuse me.
Yes, sir.
So you just said that we would have to multiply our x span distances by
1 over beta.
By 1 over beta.
Yeah.
And not multiply our y points.
Y. But remember, this is y. Okay, not x. Okay, this is y. This is x.
Yes.
Yeah. So y point is not changed. Okay, I'm sorry. This picture has an error. This is y. This is x. So x gets changed, but y does not change at all. Okay.
Awesome.
So every corner, you keep the same y, but x divided by beta. Whether it's a vortex lattice or a horseshoe vortex, wherever you have a x, it gets scaled by 1 over beta. That's what happens. So what happened to the aspect ratio of the wing? We notice that the wing area has increased. Okay, wing area is projected planform here. We notice that everything has gotten stretched. So you have a bigger chord, same span. So the area of the wing, this new wing, is going to be 1 over beta times area of the old wing. Okay. Aspect ratio is span squared divided by wing area. Span is the same, so span squared is the same. But because the wing area has changed, the compressible wing has got a lower aspect ratio than the incompressible wing. Okay. So compressible wing aspect ratio is 1 over beta times incompressible wing aspect ratio. So aspect ratio is span squared divided by wing area. Span stays the same, wing area increases because of the Gothard's rule, Gothard's transformation. Right? Now then Gothard said, okay, let me take a look at the boundary condition. Phi is capital phi, x got stretched. eta and zeta didn't change at all. Same airfoil, same camber, same alpha, everything. Then phi became capital Phi, z became zeta, so left side became, d phi d zeta. V infinity can be kept the same because we never worry about dimensional quantities. That means it follows that this body slope in the compressible plane must equal the body slope in the incompressible flow plane. That means it's the same body, same airfoil everywhere, same twist. Okay, so if you have a 5-degree angle of attack in your incompressible flow, when you do it here, you'll do it 5-degree angle of attack. Nothing different than that. Okay. So on your right-hand side, remember you had a minus V infinity times alpha. There, that alpha will not change when you go from compressible flow to incompressible flow. The body slope does not change at all. Okay. So after you have done this, we are interested in the CP. So same thickness, same camber, same angle of attack, same airfoil. Only the wing planform has been altered by stretching the cord. Okay. I highly encourage you to run the program, print out stuff, compare with the AVL, visualize your plot, make sure everything is working. Don't just go for one number. Okay. Don't try to work backwards to change here and there the code. It may work for one case, but it won't work for everywhere. So you need to have a logical way of doing it. Okay. So use the AVL as your guru. Okay, I am devil's advocate, so don't come to me. Okay, go to AVL. So how about the CP? Again, X is changed, phi is capital Phi. D phi dx becomes d phi dx times 1 over beta. Therefore, the CP equal to CP incompressible by beta. So change the compressible wing into an incompressible wing. Run your vortex lattice program. Get CP anywhere on the wing. That's going to be CP incompressible flow by beta is the compressible equivalent. That means all the lift you get from your incompressible problem, all you have to do is divide it by beta, then you get the lift. If you wanted a lift curve slope, do 1 over beta times the incompressible. It's not the same physical wing though, it's a modified wing. Okay? So you can't take your homework number 2 and divide by beta. It won't work. You have to stretch the wing, analyze it, get the 2D incompressible answers, then divide by beta. So this is how we will do it. Okay? So this in a nutshell is Gothard's rule. Okay? Gothard also said, as far as the induced drag is concerned, by the way, L prime is going to go this way. L would be L incompressible because in the y direction nothing gets stretched. Then the CL would be lift divided by 1/2 rho V infinity squares times wing area. Because the wing areas are now different, you get the CL scaled by beta also, wing lift coefficient. You could also show that the induced drag gets scaled by 1 over beta also. So if somebody gives you this